Okay, I neglected to see the D and E part, so sorry about that. All right, I think it's important to go over. Now, hey, if you're already done with this, quietly work on something else. Okay, so now we've got this loop that's outside the solenoid. We want to know what the induced EMF is on it, and maybe I'll just do it right here on the paper. All right, so the induced EMF is, always write down the basic equation, okay? Because even if you screw it up, you're going to get a point or two. And a point or two can make all the difference. All right, so, but hey, remember this, that this is the rate of change of the magnetic flux where there is magnetic flux. All the magnetic flux is in the side of the solenoid. Outside the solenoid, there is no magnetic flux. So this is going to be negative, so this is D. This is D dt. B, and B times A. And what did we say B was? For B is mu naught Ni times A. But now here's what's different. A is different. It's pi r1 squared. Is that clear to everybody that it's pi r1 squared? Not pi r3 squared? Right? Because there is no magnetic flux outside the solenoid. So there's no changing flux outside there. So if you use R3, you get it's too big. All right. So, and this just becomes basically the same answer we had before. Mu naught n pi r1 squared, because those are all constants. And this becomes di dt, but it's delta I over delta t, which just becomes I over t. 0 minus I over t. So the negative goes away. So I do that right? I hope so. Did I leave something off? I feel like I'm leaving something. Okay. And then part E, the magnitude of the induced field at a point in the loop. Now this one really is a little bit different. This is E dot ds. Now it's going to be equal to all of this silliness. Now here's the difference between just writing down an equation and actually understanding what the equation is. I mean, what it's telling you to do. Okay? See this closed loop? It's a closed loop where? Yeah, where the charge is feeling the force. Where is the charge feeling the force? In this loop right here. That's where the little charges are. It's up here. They're getting pushed around in there. So you have to say, well, E and the total distance, the closed loop distance, is just the circumference of this guy, 2 pi r3. So the pi cancels, and you still divide by 2, but R3 does not cancel with R1. So you have to divide by R3. And there's your answer. So let's just, am I still on camera? Yeah. So this is just going to be mu naught n R1 squared I over 2t R3. And there's, now what is this? What is this? This is the electric field. That's the electric field in this loop. Okay, so again, when you're correcting this, don't just write down the solution. Try to take a step back from the problem and look at what the big ideas are here. And these are the biggest ideas in electromagnetism. Okay, Ampere's law and Faraday's law. And I mean, those are two of Maxwell's equations, and Maxwell's equations describe all of classical electromagnetic theory, and they're the basics of everything beyond. And I know it's crazy and weird, but it's doable. You just have to keep pushing yourself to do it. So, and think a lot about it. Anyway, now I think I really am done with number 3.